Okay, cool. We're recording. How's everyone doing?
Well, you know that error I talked to you about on the the phase shift. I couldn't get it below 3 days in terms of
Right.
the.
Yeah.
So all last week I couldn't get that computer to do it, and this week when I went to finally get it recorded, now it's working fine.
Yeah. Those are my favorite bugs, the ones that fix themselves.
I mean, I tried it probably 4 times last week, just starting the computer and everything, and so I thought, okay, I got some time this week. I'll try to record it, and I went in to record and it was going down to point one and everything. So,
Hmm. I have no idea.
yeah,
Yeah, no one's ever reported that bug before, so if you can't reproduce it, I'm not going to worry about it. But if it comes up again, yeah, give it a recording and we'll see
yeah,
what we can do. Let's see. I am recording, just double checking. Yes, I am. Okay. Let me share my screen. Spread you out. So, welcome to Seth. Seth is checking out our curriculum. He, Seth, you were a grad student at UNC a long time ago, right?
That's right. Yeah, I got my PhD in 2011. And so now I teach at Earlham College. I teach astronomy, but I was actually not an astronomy grad student. I was studying general relativity, black holes and theory. But now I'm teaching students astronomy. So I was talking to Dan the other day about trying to make use of all the great resources y'all have.
Okay, so right before we started, I was adding Seth to my sample section, and so your username and institution has been added to the WebAssign database. So let me just finish this up here.
Fantastic.
Yeah, it's hard because these things are set up to add people at your own university. And so when
Hmm.
it's someone at a different university, I have to guess at the username and guess at the institution. And there's all sorts of variations. Sometimes the username is the full web address, email address. Sometimes it's not. Sometimes the institution, if it's smaller, they do dot and add the state. So I have
Right.
about like a two-thirds chance of guessing it, but it did seem to work out. Let's see. You just have view access. 'Cause this is one of my active sections with students.
That's great. I mean, just being able to see what all the labs are and stuff
Mhm.
is huge.
Okay, granting you access. Should we pop up here? Okay, there you are. Excellent. Okay, let me get back. Um, okay. All right. So let's get started. Let's see here. We are up to lab 7. So let's see where we are in the recordings. Here are the recordings from this semester. Lab 6, I added that right after the session last time. Lab 7, I'll add that today as we get through it. Previous labs, so we're almost done. Lab 7, which is the unusual lab. This is the radio lab, the spectroscopy lab. Then where we measure the rotation curve of the Milky Way. Then we get into cosmology. Lab 8 is the Hubble Law Lab on the true nature of the expansion. It's one of our labs where we address misconceptions. Lab 2 being the other one, the misconceptions about the seasons. Here with Lab 8, it's the misconception about what the Big Bang is. Excuse me. And then lab 9, that's the new lab, that's the capstone lab, where we combine bits from labs 5, 6, 7, and 8. In lab 5, they learn how to use standard candles, so measure distances. Lab 6, they practice it doing the Great Debate of 1920. And so, and then in lab 7, they learn how to measure redshifts. And we combine that in lab 9, along with the concept of what the Big Bang is in lab 8. So lab 9, they're going to measure Hubble's constant. And so to measure Hubble's constant, you need to be able to measure distances. You need to be able to measure redshifts. And so they're learning how to do Doppler redshifts in this lab that will transition fairly easily into cosmological redshifts. They've learned how to measure distances in the previous labs. So there'll be this capstone lab where they measure Hubble's constant just from a single galaxy. So there'll be some uncertainty with it. But everyone in the class would do different galaxies and you average them together, you get a good Hubble's constant. And they also measure it using the CMB, so a little bit of Hubble tension. So the capstone brings all these labs that we've been doing recently together. Okay. So lab 7, these are the videos that are linked in the lab. As usual, we have the 3 introduction, background, and procedure videos. And notice that the background video for this lab is pretty lengthy. This lab, so it's a little unfortunate for Seth, he's coming in on the most unusual and different lab. So this is a bit of an oddball. The other ones are a little bit more straightforward, a little bit less background, a little bit more procedure. This one's flipped, unusual in a number of ways, as we'll see. This has a lot of background. And we'll talk about the pros and cons in just a. I'm looking at my notes over here. When does this come up? Yeah, we'll talk about all the ways in which it's unusual and pros and cons in a second. But yeah, it has a little bit more background. If you're doing the labs in connection with the lecture, a lot of the background is stuff that you cover in lecture, like the Doppler shift and what it is, and aspects of galactic rotation curves, etc. So if you have that advantage, you can offload a lot of the background to the lecture periods. If not, you could do just more background during the lab period. The counterpoint is the procedure section is pretty straightforward. So once you've done the heavy lift of them understanding everything that's going on, they can execute it pretty easily and touch on dark matter. So that's the carrot for this lab is dark matter. The carrot for the next lab is dark energy. Okay, let's see here. Okay. So we're in lab 7. I have it loaded up here. Let me scroll up to the top. Collapse these sections for the time being. Okay. So here's the usual stuff at the top of the lab, the links to the introduction, background, and procedure videos. For Seth's sake, all the labs have this up at the top. And, the introduction is just like a nice 2-minute intro as to what they're going to be doing. The background and procedure, it's nothing unique. I just basically go through the background and procedure sections like I'll do today, but a little bit slower and more detail. And it's for students who don't like to read, which is most of them these days. Yeah, but it's also there and all the videos are there. If they learn something in lab and then it's like a week later and they're writing up their results and they forget what you said, they can go back and watch videos of me saying similar things. Okay. Then we have our link to the observing guide, and they go here to figure out what observations they should place at the beginning of lab that they'll need in the next lab. And the next lab is one of the concept labs that doesn't require Skynet data. 2 of the 9 labs don't require Skynet data, so no observations to place this week. The reminder to go back and check sources of error in the previous lab. Again, students keep doing the sources of error. And if they don't go back and see why they're losing points, they'll never get better at it. So there's always the reminder there. And then all the standard reminders that we've gone through before. Okay. So here we are at the top of the lab. Let's go through the goals first and then some of the boxes this lab checks. Uh, First goal is measure speeds, the speeds at which matter orbits the galaxy, and in particular, it'd be gas, not stars. We'll be looking at 21 centimeter emission line coming from cold hydrogen gas, which is the most abundant thing in the galaxy. And this is a radio emission line, so they're going to get their first exposure to radio. But as you'll see, spectroscopy is way easier to do in the radio than it is to do in the optical. So this is a nice way to introduce them to the radio. But this is Doppler shift, and that's important because it's a primary concept that we rely on. But also in the next lab, we'll be talking about cosmological redshift, and they're different. They're measured the same way, but they're fundamentally different. It's hard for them to understand how they're different if you don't first explain Doppler shift. So that's one of the boxes in my upcoming list here. Goal number 2, measure the rotation curve of our galaxy and use it to determine if the mass is concentrated, like it is in the solar system, or spread out, like it is in most galaxies. And you get different rotation curves, like in the solar system, you get a Keplerian rotation curve where things close to the central body go fast, like Mercury, and stuff far away move more slowly, like Neptune. That's kind of their expectation, but they'll see here that they don't get that. They get a rotation curve that ramps up and stays flat. Again, typical of galaxies, and that's because the mass is distributed. It's all about the enclosed mass within your orbit, as we'll see. Okay, so rotation curves, that's a fundamental concept. And the third one is the mass. Once you have the rotation curve, how fast it's rotating or orbiting, I should say, at any given distance from the center, you can calculate the enclosed mass, how much mass is within that orbit. So they're going to weigh the galaxy, and which is pretty exciting. They only took 12 observations. We went through placing those observations last time. I think I recommended 10-second exposures. I watched the video today, and in the video I say 5-second exposures. In the write-ups and some of the tutorial videos, it's 1 or 2 second. But as I mentioned last time, those shorter exposures sometimes jam up the radio telescope at Green Bank. So we've been recommending like 5 to 10-second exposures. But still, if it's 5-second, 12 spectra, that's a minute. In 1 minute's worth of data, they can weigh the whole damn galaxy. And so that's a pretty cool concept.
Dan, can I ask a question real quick?
Yeah.
So you were saying, so they're not taking data this week, but they're using the data they took last week? Is that?
Yeah. Every week you take data in advance for the next lab.
Okay.
Yeah.
Okay, but this lab is special in that you're not doing observing, or am I?
Yeah, that's right. No observing because we don't need data for lab 8. Labs
Okay.
2 and 8 are cure this misconception, build up this concept.
Right.
Lab 2, we use globes and lights or stellarium if you're doing it online, and which most people actually do. And in lab 8, actually, in fact, I'll pause and actually hop over to lab 8. I'm glad you said that, because even though we're not taking observations, there are some supplies that you'll need. And so let me mention those, and then I'll come back and talk about the boxes that this lab checks. So yeah, normally at this point in our training videos, we hop over to the next lab and learn how to place the observation. Here's lab 8. Instead of learning how to place the observation, I'll just go to the equipment line and let you know what supplies you need to make sure you have ready for next week. And unlike lab 2, again, most people do the online stellarium-based version, which doesn't cost anything. But if you're doing the globe and lights version, it can be a little bit costly for those setups, particularly if you have to build PVC cages to block the light, etc. But here in lab 8, the supplies are all very inexpensive, and so you should be able to acquire these pretty easily. You need foam board, because you're going to be taking this rubber band. The rubber band is a one-dimensional universe. You're going to draw some evenly spaced galaxies on there and do measurements that we'll talk about next time for both uniform expansion and accelerating expansion and decelerating expansion. where the students have godlike powers. They can stop time, pin the universe, make their measurements, and then move to the next position. So foam board is good. You want push pins. Thumbtacks are not as good. Regular pins not as good. So you want push pins. And rubber bands. It can't be any rubber band. It has to, when you cut it, it has to be 18 centimeters long. Uh, you want not to be too thin. It needs to be kind of thick. It needs to be a good, sturdy rubber band that's not going to break. Uh, if you're ready to get parts, just email me and I can send you the parts list for Lab 2 and Lab 5 with Amazon links where you can get this stuff. But the only thing you really need the link for is the rubber bands if you want to make sure you get the right kind. But they're standard rubber bands. When they're closed, they're about 9 centimeters. Excellent. You got yours. And you cut
Dan,
them.
it's the size I found that worked best was called a number 64 rubber
Number
band.
64 rubber band. That's good to know. Great. And those are nice and wide. And
Yes.
that's good. Yeah, if you get cheap, crappy rubber bands, they can break and then tacks or push pins fly across the room. We've actually got safety goggles. One of the things not listed here, I got safety goggles for my students. So I don't, it's all fun and games until someone loses an eye.
And I built I ordered cork board on
Nice.
Amazon, and it's got a epoxy back on it, so I put it on thin plywood.
Very nice. And that's nice and thick too.
Yes.
Say with the foam board, you stick those push pins in and you hit the table. So you actually have to slide the apparatus over the lip of the table. But you're not going to have that problem. Okay, so Ken has the most advanced Lab 8 setup. What else is on the list? A marker, a scissors to cut the rubber band, and a ruler with the centimeter scale. A foot long ruler, but it has to have a centimeter scale. And that's it for Lab 8. We'll come back and talk about that. Next time, I rather like Lab 8. I spent a lot of time playing with rubber bands, making sure everything worked and it fit within a standard ruler and it wasn't stretched so much that it would break the rubber bands usually. And it works out really well. It's a good conceptual lab. But anyway, make sure you have those supplies instead of putting in observations, go supply shopping. Okay. And with goal 3, I said we're going to measure the mass. That's actually the mass distribution out to any given radius. You can measure the mass. And then we throw in the LMC and SMC, and their speeds and distances are measured by other techniques. We're not going to do that here. We just give them those extra points. And so as they're calculating enclosed mass, we can do so well outside the visible disk of the Milky Way. And that's how we're going to touch on dark matter. Okay. Equipment for this one's just the computer. So before I get into the background sections, and you can see there are a lot of them this time, the boxes that this lab checks. First, we're doing spectroscopy. In most introductory lab sequences, you have a spectroscopy lab, and usually you are looking at like a hydrogen emission lamp with some kind of disperser, like a grating or a prism and measuring wavelengths or something like that. And that's really kind of boring. But, what else can you do unless you get fancy with telescopes? And this is what we do here. And as I said, optical spectroscopy is a little bit more challenging. Radio spectroscopy is really easy and it happens automatically, even if you don't want spectroscopy. If you're just integrating light over a frequency band, you get the spectrum for free. And so spectroscopy. Another box that checks is radio. So far, all the labs have been optical. Lab 9 will also have some radio. So the skills we're learning here will be applied again. If they go on to the MW curriculum, it's 50% radio. And this is really kind of important because we really, in our lab courses, we really lean towards visible because one, it's what the eye works at, but it's also the telescopes we have. And it's the astronomy the students are familiar with or at least have some intuitive feel for. And we all have campus telescopes or small telescopes, and they're all visible light telescopes. A small radio telescope is bigger than a building. And so they're very expensive. Campuses usually don't have them or run them. Governments build these things and run them at national observatories typically. They're very expensive, and they also have to be remote. You wouldn't want one on your college campus unless your campus is in a super remote location because civilization is very loud, radio loud. So, most students never gain experience with radio telescopes, even though it's the other ground-based astronomy. You have optical, near infrared, and then you have the radio regime. Everything else, the atmosphere blocks, and you have to go to space. So it is ground-based, but because of the expense, because of the remote locations, they just don't gain experience with it. And that means, you as students never gained experience. And so you as educators are not giving experience. And so that's one of the things we're hoping to cure with Skynet. Many of you know I've always been passionate about radio astronomy education. I've run a program at Green Bank since 1992. It's super exciting, and the stuff you can do with it. There's all sorts of great stuff that you could do with it that are key lessons that we learned, that we teach in our lectures, but they can't touch it in the optical. So it's a nice orthogonal way to observe the universe. So they gain some experience here. And also, the big theme of 21st century astronomy is moving out of the optical band into other frequency regimes. And so this ties in with that. What else?
Dan, quick question.
Yeah, go ahead.
Safe to say that radio astronomy is very is not very well there's I guess, from lack of a better word, dearth of educators that are versed in radio astronomy.
Yes. Yeah. Yeah. Educators, they didn't experience as a student, so they don't, unless they specifically went into radio astronomy for their career. Most educators have never observed with a radio telescope. They've looked through optical visible light telescopes of various sizes. So they just don't have the background.
So somebody looking to, say, carve out a sort of a niche, that would be a
Yeah.
interesting topic.
And so we do a little bit of radio astronomy training here. And if you train up on the MW curriculum, and I'll be holding sessions in the spring for those who are interested in offering it, you'll learn a lot more radio astronomy and how to use Skynet more deeply at visible wavelengths as well. And in the MW curriculum, we incorporate archival infrared from NASA spacecraft, Spitzer in particular. So a little bit of X-ray in one place in the curriculum. So it is much more multi-wavelength. And this MW multi-wavelength universe is the name. Okay. And then the other thing, as I mentioned before, we get the Doppler redshift, which is key to distinguishing it from cosmological redshift in the next lab. Another aspect, I have said it's background heavy. There is a little bit there's some geometry, and 3D geometry is sometimes difficult for students to visualize. And there's a tiny little bit of trig. We do have some right triangles, and everything else in this sequence is high school algebra 1 level, solving simple algebraic equations, plug and chug. But here we do have some sine functions that they'll have to use in their calculator. They don't need to have a deep understanding of it, though, and so it should be okay. Okay, and then as I said, once you get through all the background, which we're going to go through now, the procedure is pretty easy. Okay, so let's start going through the background sections. And again, I apologize. I know you know this stuff. I'll just do quick versions to give you an idea of what you may be saying to your student. So the first background section, let's see what sections we have. We have the Doppler shift, the 21 centimeter emission line, radio spectra, how to interpret the radio spectra that we get back and see that 21 centimeter emission line with the various Doppler shift components, how to measure radial distances and orbital speeds from that spectrum, and then how to calculate the mass distribution. Again, as we go through this, think about the parts that you could do during lecture, so there's not so much upfront at the beginning of lab. So the Doppler effect, pretty simple. In the first figure, we have a stationary source. It's emitting. The blue circles are the crests of the waves or the troughs. It doesn't matter, but I tend to think of them as the crests. And since it's stationary and we have stationary observers, you can see how old this figure is because we have space shuttles in it. All these expanding circles are centered on the same point of emission. So the spacing that is received is the same as the spacing that's emitted. But here we see it moving, and the circle that was emitted at time 1 is now out here at time 5, and it's centered on its point of emission. Same with 2, 3, 4. These circles are centered on their point of emission, which makes sense. But since the point of emission is moving, they get compressed in the direction of motion. Shorter wavelength is observed than was emitted, or in this direction, away from the motion, opposite the motion, the waves get stretched out. So the observed wavelength is the emitted wavelength minus or plus delta lambda, minus if it's moving towards you, plus if it's moving away, where delta lambda is the Doppler shift equation, the emitted wavelength times the velocity divided by c. Now, in our lecture courses, we often simplify this and only consider things that are moving directly towards you or directly away. In this unit, they have to think about components, because often, we're over here, we're looking at some blob of gas in the galaxy, and it's moving in some direction that's not towards us and not orthogonal. If it's towards us, it's blue shifted, or the negative red shifted. If it's orthogonal, no shift. But if it's at some angle, it's just the component of this along the line of sight that they're measuring. So that's the little twist that we have to, it's like stepping it up a level from the simple problems you may assign in lecture to a real laboratory experience. Okay, that's Doppler. Now the 21 centimeter emission line. So here's a panorama of the Milky Way. It's full sky, so you can grab the left and the right and wrap it around. Well, not the full sky up and down, but 360 going around in galactic coordinates. Wrap it around your head. And so that's the plane of the Milky Way. And the primary feature we see here are the dust lanes. And dust, the largest grains are about a micron. And the way it works is if light waves are smaller than the dust, it gets absorbed or scattered. And if it's bigger, it can make it through. So 1 micron, that's the boundary between visible and near infrared. And so dust can really wreak havoc on what you can see at visible wavelengths. Because the visible wavelengths are shorter, they get absorbed or scattered. And so we see the dust lanes where we see nothing. And even the stars that we do see behind them, they're relatively nearby because there's dust in that distribution blocking the stars that are even farther back. So most of the stars we see are nearby just because of dust. And so if we're going to try to probe the motion of the galaxy, it won't work at optical wavelengths because we're not actually probing very deep into the galactic distribution. But if we look at wavelengths longer than a micron, we're good because those wavelengths are bigger than the dust grains and they go through as if they're not even there. It's the same thing as why the sky is blue. Short wavelength stuff scatters around. Now, longer than micron, you're into the infrared. Near infrared's really tricky to do. We don't have any of those on Skynet at the moment. And then mid and far infrared, you're kind of going to space. The next time you're back on the ground is the radio. And there we're going to focus on the 21 centimeter emission line. So its wavelength is macroscopic. It's this big, and it doesn't care about any dust. And so we can see all the way through the galaxy in the radio. So that's why this kind of measurement's done in the radio. And what we need is an emission line. A continuum emitter is not going to be any good because we need to see how the spectrum's shifting. Just like at optical, you need an emission or an absorption line, and you can measure its shift. Now, the students are used to lines produced by atomic transitions. They've learned the Bohr model of the atom over and over. So, hopping from the first excited down to the ground, or the second to the ground, or the second to the first, etc., gives you visible light photons, gives you ultraviolet light photons if you're going deep into the well, and infrared photons for higher up transitions. But this radio emission line is a little bit different. It's not due to a transition between levels. It all takes place in the ground state. This is the spin flip transition. And, I often will bring bar magnets with me to class when trying to explain it. So we're talking about hydrogen. Hydrogen's the most abundant gas in the universe. And we're talking about cold hydrogen, because if it was hot, it'd be bumping into each other and the electron would be pushed up to higher states. So this is cold, neutral hydrogen gas, the most abundant thing in the universe, most abundant thing in the galaxy. So great. And in there, in the ground state, you have an electron and you have the proton at the center. And they're charged and they're spinning. And if you have spinning charge, you have a magnetic field. And we see this on all scales. Like Earth, we have, ionized iron moving around in the core, accretion disks around all sorts of astronomical phenomena, up to like active galactic nuclei. Uh, it's hot, the disk is ionized, the moving charge, you get a magnetic field in the orthogonal direction. And the same story applies even with the proton and electron. That's the simple version for a student, anyway. And so they're little magnets. And we've all played with bar magnets, and you can hold up your bar magnets. And if they're aligned and you try to hold them together, it takes some energy, it takes some work to hold them there. But if they're anti-aligned, they, want to stick together. So lower amount of energy. And the same is true for the proton and the electron. When you're in the aligned configuration, it takes a little bit more energy to be there. It's going to want to flip down. So these things are charged up, excited just through gentle collisions. You just have a gentle bump of the atom into something, another hydrogen atom, and that's all the energy you need to go from here to here. It's a very small energy transition, corresponding to just a 21 centimeter radio photon. It's hardly any energy. And then it will decay, and its half-life is 11 million years. It's a really long half-life. And so you may think, oh, I'm never going to see any of this, but there's so much cold neutral hydrogen out there. The signature is overpowering. It's super strong. Okay, so that's the nature of the emission line. And here's a map of the Milky Way at 21 centimeters. And so this is showing you where the cold hydrogen is. It's all in the plane of the galaxy. That's where the stars form. They form deep in the plane. And, we don't see anything else. If you had a good map, you can sometimes make out Andromeda over here and the Magellanic Clouds over here, but I don't see them. But there's the cold gas of the Milky Way. Okay, spectra. So let's think about what these spectra will look like. We've already acquired them, and I think in the next section we see how to load up our data into the analysis tool. But let's just think about what they'll look like. This is galactic coordinates, so if we're looking right here, we're looking at the galactic center. And this is both the easiest line of sight, because there are no Doppler shifts, as you know and as you'll see, but it's also the most complicated line of sight, because we have a lot of continuum. There's a lot of stuff emitting radio at the center. So there's a big continuum. So you can have absorption as well as emission that you won't see along the other lines. But the first line of sight they got was galactic longitude 0. Here's a top-down map of the Milky Way. This was actually made from the exact same data they're acquiring. Hydrogen and also carbon monoxide spectra, they were able to work back through all the Doppler shifts and some other techniques and make this map. And then they hire an artist to pretty it up. So sometimes when a student sees this, they can have the misconception, oh, we must have a spacecraft up there looking down. But, here's the sun. In the previous lab, we learned in lab 6, we learned it's not at the center, it's offset. So we'll start to use something we learned in that previous lab. But all spacecraft we've ever sent out have never even exited this pixel on this picture. So that's often a good thing to point out, that this is a reconstruction, and it may be off at the 10 to 20% level. And this is hard to do. So it's a decent picture of what the galaxy probably looks like. Anyway, here's the line of sight, us looking at the galactic center. Because dust is not a problem, we're collecting information from everywhere along here. So I've drawn a little arrow wherever we cross an arm. We have a pileup of that hydrogen gas. And since we're looking at the center and everything's going around kind of in a circular fashion, all these intersection blobs of gas are moving to the left, and all these are moving to the right. None are moving toward or away, so you expect no Doppler shift. You should just see the hydrogen line. And when the students load their data into the tool, for this line of sight, you're going to have to provide a little bit of extra explanation. So here's that hydrogen line. It comes up, and I've kind of filled in the gap here, and it comes down. It's a broad emission line. But since we're looking at the center of the galaxy and there are really bright radio sources there that are emitting, this whole spectrum has been raised. It's sitting on a high continuum, and the same gas that can emit can also absorb. And so the gas between the center and us, it's absorbing, and here it is right here. So you have an absorption line right on the middle of a wider emission line. So that makes it a little complicated. They're like, which one do I use? They actually want to use the middle. They can use this point right here to figure out its wavelength. And here's another absorption line. So this is from a cloud of gas that's moving towards us. It's more blue shifted, shorter wavelength. So there's just another cloud of gas absorbing this light as well. So this spectrum, the first spectrum, the zero spectrum, is a little complicated. It's easy because no Doppler shifts, but complicated because the absorption lines. Okay, so let's consider another one. This one is offset. Remember, they're doing 12 of these from 0 to 88. That's where the trig of this exercise works. So here's a visualization of that. We're looking off in this direction. I've drawn arrows wherever we intersect. And there's a special point right here. It's the point of maximum redshift. Basically, these arrows are circles. Imagine, at this point, what's this? If you draw a circle through the center of the galaxy, through that point, that's the direction the gas is going. And so only at this special point is the motion of the gas lined up with the line of sight. So we get the maximum redshift at this special point. And that's great because you could probably already see it. We have a right triangle between that special blob of gas, the most redshifted blob of gas, the center of the galaxy, and us. And so we'll be using that right triangle. And so in the spectrum, they're going to see the line multiple times. Here's an example of, I think, this particular spectrum. And this most redshifted one corresponds to that special point. The other ones are, either the arm that we're in or nearby arms or farther away arms, just with different shifts. And they'll be less because only the component of that velocity vector, it shows up as a Doppler shift. I should also point out that it'd be a little bit blue shift, like this one right here. It's almost orthogonal. It has just a small motion away from us. You may expect a small redshift, but remember, we're also moving. And so the component of our motion along the line of sight is actually bigger than its component away. So that one actually comes in as a blue shift. Anyway, so the most redshifted point, and there's a lot of freedom here. Some of these spectra are confused. You have arms on top of each other. They're not always well separated like this one. They can measure it here. They can measure it halfway down. They can measure it at the bottom. They just have to be consistent. The autograder is set to be very, very generous. And it's not always the brightest one. It's the most redshifted one. I'll show another example in a second where the most redshifted one is not the brightest peak. And so that's another mistake students often make. They go for the brightest. They want the most redshifted. Almost there, almost through the background. You can see there's more of it. Okay, once they have their spectrum, how do they measure the distance from the center and the speed? So we're focusing on that special blob, the most redshifted point. We're going to measure its distance from the center and how fast it's moving around the Milky Way. Distance from the center is easy. We learned in the last lab doing the Great Debate of 1920 that our location is about 8.1 kiloparsecs from the center. And we know the galactic longitude that we took the spectrum at, that we pointed the telescope. And so its distance from the center is just 8.1 kiloparsecs times sine L. So again, this is where there's a little bit of trig. They don't really need to know sine functions. They just know it's a magic button on their calculator. They have L in degrees and the calculator's in degrees. They type in the angle, hit sine, and it's a magic function that gives us that side of the triangle. That's really all they need to know, the opposite side. Okay, so that gives them the distance of the blob from the center. Now we just need to know its speed. This one's a little trickier because there are two parts. So here's a spectrum. This is at 16 degrees. The most redshifted point's not the brightest point, but there it is. And so they measure its wavelength. They got to measure it to 4 decimal places because it's that accurate and we need that level of accuracy. And they plug it into the Doppler equation. And so they get a speed and they subtract it off because it's redshifted. So the observed wavelength the observed wavelength minus the emitted wavelength, that's delta lambda. And yeah, we're just calculating that. Sorry. We'll do the velocity. What am I doing here? Okay, sorry. Got it now. They measure the wavelength, they stick it in here to get the change in wavelength, and then they calculate delta V using the Doppler equation. Okay. But that's just the relative motion. That's just its motion. Here's the blob here. That's its motion from us. We also have to add to that our motion along the line of sight. So that's the little twist here. We're moving about 220 kilometers per second around the galaxy. This was determined by measuring our motion with respect to a bunch of galaxies around us. So our motion along this line of sight is 220 kilometers per second sine L. So they have two things they have to measure. Delta V from their spectrum, which is the relative speed along the line of sight, and then they add 220 sine L, and that's the overall speed of the blob, the special blob going around the Milky Way. So they have their R's, they have their V's, they have a rotation curve. They plot that up, and we'll see more of that in the procedure section. Once you have the rotation curve, the last thing is getting masses. So I start with a little example here. Here's Earth going around the sun. If the sun's mass were to suddenly go to zero, we would just fly off on whatever vector we're currently traveling on. The sun's mass were to go to infinity, would whoop, be pushed, pulled right in. And so clearly our orbit is a function of the interior mass. And that's just a way of motivating that concept. And Newton figured out the relationship. The enclosed mass is equal to V squared R over G. They just measured V. They just measured R. G is a constant. So this is a very natural thing to calculate. Newton showed it is a function of the enclosed mass. If you have mass out beyond and it's evenly distributed, it cancels out. Suppose this isn't the solar system, but the Milky Way. So there's clearly going to be mass out beyond us. But on the other side of the circle, there's covering the same angle, it's a lot more mass, a lot larger region, and more mass. It's farther away, but the effect cancels out. So Newton showed it's only the enclosed mass that matters. Here's the relationship. You can turn it around and solve for V. So in the solar system, all the mass is in the sun. The planets don't weigh anything. And so the enclosed mass is always m sun, and you get V is proportional to 1 over R to the 1/2. So that's your Keplerian rotation curve. The planets going around the sun, moons going around planets in the solar system, they follow that. Neptune orbits slowly, Pluto orbits quickly. With galaxies, and I would say with some galaxies, it's actually with like all galaxies, but we don't want to give them the answer in advance. You can say with some galaxies, the farther you go out, there's more and more enclosed mass. It's a disk of gas. And so there's gas there, there's mass there. The farther out you get more. And in some galaxies, it's proportional. You go out twice as far, you get twice as much. In which case, the enclosed mass, if it's proportional to radius, that cancels with the radius, and you just have a constant. And it's called a flat rotation curve. After an initial ramp up, it's pretty flat. So these are the two cases. And if they measure a flat rotation curve for the Milky Way, that tells them the mass is distributed. It's not all at the center in like the central massive black hole. And that's another misconception students have. They think that black hole at the center of the galaxy is most of the galaxy's mass. It's not even close, right? It's what, 4 million masses, our central black hole, but the galaxy is like 100 billion stars. And so I forget the exact mass, but way, way more than that. Okay, those are the background sections, a lot of background. So again, but you saw a lot of this is fundamental stuff you teach in lectures. So you could probably offload some of this to lecture. If not, you have to do it in class. It's okay because the procedure is fast, which is also good because I have 16 minutes to do the procedure. So here's the section where we place the observations. We went through this last time. It's in the previous video. So now let's do the analysis.
So I know you have 16 minutes.
No, and we're good. We're
good. So
ask away.
Are they not placing the observations here in that previous section?
They did a week in advance.
Okay.
Yeah,
So they are
lab. Yeah, you have to hop to the next lab.
They'll say, "Oh, I did that last week."
Yeah,
that's the way they'll interpret it. Okay, thank you.
Every lab we have to hop to the next lab, which makes training really confusing. I set up lab N, and then we immediately talk about lab N+1, and then we come back and
yeah.
So they already have this data, and we'll see what it looks like because we'll see what it looks like right now. There's a tutorial, there's a website. I already have the Astromancer site up. Let's go to Skynet, radio observing. I put some in last time. Let's see. We did galactic longitude 0 and 8 just as a sample last time. So here it is. These are Greenbank's data products. In Skynet 2, we'll have our own data products page for this stuff. But right now, we just hop straight over to theirs. Here you can see that high resolution spectrum. They're in frequency here, but we're going to download this. You go to calibrate, right click, save link as, just save it. Might have to press that keep. Okay. And then the other link takes us to our Astromancer collection of tools. We'll be using the Spectrum tool here. I have one in from before, but let me just upload that new data set. Because if I recall, there might be a small... Did I dump it in here? I guess I did. Okay. And so if we look at this, it's now been flipped around. You see that pattern here. We flipped it around because we decided to do this in centimeters. Because think about how we motivated Doppler shift. We're talking about how the waves are shorter, longer. So we're talking about wavelengths. So this converts it to centimeters. So it's now flipped around. It zooms into the region of interest. It just makes it a little bit easier for them to measure stuff. And they're looking for the most redshifted one. For some of the early ones, there is some stuff over here. And so I would probably pick this as 21.1197 would be my number. But some people may say this. And for the early ones, the most redshift emission is really faint. So some people may do this. And I've set up the auto grader to accept that stuff as well. So it's very generous on these first couple where it's not as clear. Okay. In the first couple, it's going to be the ramp up of the curve, not the flat part. So anyway, it's very easy to measure here. If the one channel is dead, we do have two channels on the radio telescope. Again, remember, it's a 1-pixel camera. And I think we talked about the telescope last time. Let me just pop back to lab. Just re-emphasize. 6 stories tall, 150 tons, 20-meter collecting surface. It's a small radio telescope, but it's bigger than any visible light telescope. And they're pushing this thing around themselves, the students, which is pretty cool. Okay. Anyway, sometimes one of the channels dies. And so you may have to go to the other channel. And the little wiggles and stuff, it's all real. The noise level is super, super low. So, you're really not dealing with that kind of source of error. Okay, let's go back to the lab here. So for each one, they're going to insert their measured wavelength. They're going to calculate the Doppler velocity, the relative speed of the most redshifted point, that's the right angle point. They're going to calculate 220 sine L. Going to add them together. That's their velocity, and they're going to calculate the radius. Now, we give them a spreadsheet and a video on how to work with spreadsheets. We started introducing spreadsheet stuff last time. I think I have it up here. So it's partially formatted. We don't have the equations coded in because then it'd be too easy. Let me just put some random numbers in here. I don't know if those are real or close or whatever. And anyway, they fill in all of them there. Oops, sorry, my bad. I'm already screwing this up. Okay, wavelengths. And here, so they observed at these different longitudes and degrees, except in Excel, they work in radians. So we have to convert, divide by 180 times pi. Remember, pi, you have to close the parentheses for it to actually take. And then they drag on down. Don't know why my spreadsheet's so slow. Okay, so that's converting the degrees to radians. They'll need that for the sine functions. They input their measurements here. Doppler shift. So, this is the observed minus the emitted, divide by the emitted, times the speed of light. We give them all the constants over here. Now, there are two ways they can do this. If I were to just do that and drag it, as many of you already know, it's gonna keep shifting to the new lambda obs, but it won't hit the right boxes for the constants. If we want those constants to stay, you have to add a little dollar sign. Else, as I drag it down, K3 becomes K4, K2 becomes K3. So that's one way they can do it. They add the dollar sign. Then when they drag, my computer needs a serious reboot. I kept those, but changed this one. Now, if that's too complicated, they could just use this table over here to see what the values are and just type them in. And probably most will do that. It's least prone to error. Same number, drag these, and I clearly picked some pretty terrible observed wavelengths because those are not good numbers. But anyway, you get the idea. That's the relative speed. Then the sun speed, that's 220 times sine of the radian galactic longitude. And they'd be dragging all the way down because they're going to have measurements for all 12 spectra. Total velocity is just the sum of these two, the relative speed to us and then our speed. And radius is the 8.1 kiloparsecs they measured last time times sine of L. Okay, so they build that up and they can plot velocity versus distance from the center, and that's the rotation curve. And we'll come back to this for the mass and for the last bit in just a second. And once they calculate those, they enter them here for the auto grader. This is an answer key view, so they won't see all the green boxes and X's. It's a very clean table for them. They assign their name. They upload one of the spectra. We ask them to upload the last one and provide a sample calculation for each of the things they just did. And then they go back to the graphing tool and they go to the first one. And here they will, they just need one curve and they will plot, the R values on the x-axis, the V values on the y-axis. And, you can edit the labels and everything here and then save the graph and it signs their name. So that's embedded in the EXIF data. So you can check and see if they actually did it themselves or if they're submitting somebody else's work, as we talked about before. And where's the lab again? Here it is. And so they'll end up with a plot like this. Here you can see appropriate labels, axis and overall, where it comes up and it's clearly flat. We ask them, is it Keplerian or flat? It's flat. Does that mean the mass is concentrated or spread throughout the disk? It's spread throughout the disk. Sources of error, difficulty measuring the wavelength of the most redshifted emission, given that it's, there's a lot of junk going on in the spectrum and sometimes the arms blur together. Another possibility is maybe the most redshifted point fell between two arms. And so that's a source of error. And a third one, which hardly anyone gets, there's also the source of error. We're measuring not from the sun, but from Earth, which is going around the sun 30 kilometers per second. So there's actually another correction, but it's small compared to the hundreds, a couple hundred kilometers we're talking about. So we don't have them do that in this lab. It's a little bit too much for them. Instead, just treat it as a source of error. But sometimes they'll measure the wavelength at the galactic center, and it will be redshifted or blue shifted a little bit. And that's actually our motion. So they get the rotation curve. Now for the enclosed mass, here's the table, but again, they're doing it in the spreadsheet. Enclosed mass is just equal to V squared times R divided by G. Now, V has been measuring kilometers per second, R kiloparsecs. G is usually given to them in MKS units, so they would have to do a lot of conversion. We talked about how they're not really good at conversion. So I've converted G to these units, and it comes out in billions of solar masses. So in these units coming out in billions of solar masses, it's 4302. So we Now we'll pull this all the way down. Again, they'll have stuff in here so you won't have those zeros. And down here, we added the LMC and SMC. As I said, we add those so they can have their little taste of dark matter. Now, this technique that we're doing, it breaks down once you get beyond 90 degrees here. That's why we stop at 88. There are other techniques you use farther out. There are other techniques that you use to get the velocity and distance to the Magellanic Clouds. But these two things are well beyond the visible disk of the Milky Way. In the last lab, we showed the Milky Way is about 34 kiloparsecs in diameter. They measure it, so the radius is about 17, and these things are well beyond there. So this is how we're going to give them a little taste of dark matter. So they calculate the enclosed mass out to these different distances. This last one is essentially the enclosed mass out to our distance. A sample calculation for that same last line of sight. And then we, here is actually where we introduce the large and small Magellanic Clouds. This is taken from Tololo, actually right next to our primary prompt site. And here's where they put the enclosed mass for those two. And we point out in here somewhere that they're, it's a little bit farther down, they're very low mass. So, well, that'll be relevant in a second. We send them back to the plotting tool. And, this one here, the single curve tool. And they will plot enclosed mass versus distance in kiloparsecs. Here, there are 12 lines of sight. And remember, we're out around 8.1, so near this last point. The visible edge of the galaxy is around 17, so here. Then here we have the Magellanic Clouds. So we end up by asking them some careful questions. Using your graph, estimate the mass within our radius. So it'd be this point right here. In lab 6, we measured 17 kiloparsec radius. What's the enclosed mass there? And so they eyeball it. They'll come up in the mid 200s. Then we ask them for the enclosed mass out to the SMC. It's 900. And we have them take a difference to figure out how much mass is beyond the visible part of the galaxy and the SMC, almost 700. And they compare that in the last question to the mass enclosed within the visible part of the galaxy. And so they draw the conclusion there's more mass out beyond the visible part than in the visible part. And it's not visible by definition of visible part. So that is dark matter. And there's more dark matter out there than visible matter in here. And let's see, what were the questions? The questions, what's greater, the mass outside, the mass inside? It's the mass outside. Here we point out that the LMC and SMC don't have much mass themselves, so that's not the explanation. And so is most of it visible matter like stars and gas, or dark matter? And so they come up with dark matter. Then we have them just research and give us a little summary of dark matter, different types. I give an example here, talking about machos and WIMPs, but they often talk about other things. And we grade this pretty generously. Okay, that is the very different Lab 7. Thoughts, comments? So hopefully you saw the procedure part's pretty easy. As I said multiple times, the lift is the background. So any part of that you could do early, great. If not, it may be a little bit much to absorb. But again, the procedure part's easy and it's fundamental stuff. The whole point of OPIS is for them to do the stuff we're teaching about in lecture, not looking through through a small telescope and saying, oh, that star's red, that star's blue. Done. These are the key things we teach in lecture. And so now they can actually do them themselves. Kent.
So do you find that very few students like programming the Excel, or do they have a decent background?
I haven't heard complaints. So I'm not actually in the lab. I train my TAs and they go do it. And I train you all and you go do it. And no one's ever come back and told me that they hate coding the spreadsheets. It's such a valuable skill that even if they did hate it, I don't feel bad about doing it. And they can sit there and calculate each one on a calculator if they wanted to, but that would be lengthy, particularly in the previous lab where we had 30 globular clusters. That's a lot of calculations. So learning some basic spreadsheet skills is something that they can apply in their lives, in all of their lives, or at least most all of their lives, independent of field.
I've used it extensively in my job in networking for data analysis and being able to, like, I take a packet capture, can break it, export all the information, the different fields of the data to different cells, and then I can sort or analyze by those. So, um, yeah, there's um, a lot of what I can do is in the tool Wireshark, but the couple of things I do with Excel, when I'm
Yeah.
looking at something
It-
very unique.
and
So,
it doesn't have to be Excel. It could be it could be the Mac
right, yeah,
spreadsheet,
yeah, we use,
numbers.
yeah, like
Yeah.
saying Xerox, right? We use
Yeah.
Excel, or PowerPoint as sort of a common, back of the hand reference to spreadsheet. So,
If I recall something, yeah, recall correctly, this is something the educators wanted me to add to the lab. So yeah, I integrated spreadsheet stuff about 5 years ago, here near the end of the sequence. So yeah, it's good stuff, and we're not taxing them too much. They're learning how to type an equation and drag it.
when I would teach, sort of, CIS 110 basic Microsoft Office tools, I enjoyed that the most because it was, I mean, all the other stuff seemed trivial, Microsoft Word and PowerPoint things, changing fonts and that and whatnot. But the Excel people, like I said, they don't have a lot of experience, and I could show them how, doing conditional formatting and sorting and things like that. So really, really interesting.
My comp sci undergrad, who's amazing, I'm going to bring him in as a grad student, now told me the other day that Excel and these spreadsheet programs are now, as of a few years ago, Turing complete. This is a comp sci term. I need to look up and get the actual definition, but I think it means you can essentially do anything with them.
Yeah. Dan, so just sort of general questions about the labs.
Yeah.
So, people like us who like adopt them, is there customizability if I want to focus on something more? I know that you probably covered this in like week one, and now I'm coming in late to the
Yeah,
game.
that's totally fine. Unfortunately, with the Opus Labs, no. So with the MW, yes. All that
Okay.
right now lives in Google Docs. I'll probably make um, a prettier final resting place for it. But we're setting up a web page where each instructor, as they make modifications, they can add it, and it's a community site, and people can grab whatever version they like the most and modify it. Opus has long been a partnership with Cengage Learning, and we do charge $65 for it, and they return a chunk of that to us to cover the telescope time, and which, as I like to say in the proposals, NSF is very well aware of all the curricula they funded that disappeared as soon as the funding disappeared, and this model has worked for us since 2008. It pays for its part of the telescopes. But the flip side is even I have to go through a many months long process to edit. I don't
Okay.
have editing control, unfortunately.
Okay.
And so it's one of the things I hate about it. Um, it's not my favorite. Back in the day, WebAssign was by far ahead of everything out there. It's not anymore. It was a little company set up by NC State, but it's been purchased by Cengage, the second largest textbook company in the country. They have been very slowly improving it, but it still has a ways to go. But we're going to stick with it because I'm hoping to. Uh, I got real close, and then the people at WebAssign, the people running it, changed. The astronomy division head changed, and so I got to start over again. And I'll make the attempt once I'm done with the MW curriculum. But I want this to become one of their sponsored curricula, in which case, and NSF would love this because we'd go from like 1.5% of all astronomy students using this to like 15% because they're super annoying textbook reps. All the companies have annoying textbook reps. They would be working for us instead of against us. So I'm going to stick with it at least for another probably 5 years. And if things don't improve, and if I don't get that special access, I'll consider other platforms.
Makes sense. Thanks.
Yeah. But you don't have to always do everything that's there. You can say, we're going to do everything but this part of the lab.
Mhm. What's how much of it is auto graded?
A good fraction. So only the essays, graphs, those things you have to go in and manually grade. And probably there going to be AI tools soon that help with that. Um, all the calculational, computational stuff is auto graded. There's a little bit more that you have to do in the first lab because I never know what planets are up. And so it auto checks stuff, but then you have to tabulate what to include, what not to include. Because they could say, I observed this planet, but no, it wasn't observable. Each lab, there's less and less manual grading, and it's more and more auto graded the farther you go into the sequence.
And like the ones where you were asking them to put in a formula, were you asking them for like an Excel formula or what is
Oh,
or
the show your calculation.
yeah, what do you mean by that?
They just type out they in words or some
Okay, okay.
equation. They're just showing their work for one
Sure, yeah.
example of each calculation.
Okay. So that's something you might have to grade by hand because they might type it.
Yes, yep, that as well. And in the earlier labs, I've added links that show sample calculations. I don't have them this far into the lab sequence yet. Once I get done with MW, I'll come back here and finish my updates. But each lab will eventually they can link and see an example calculation, and that should increase their rate of success.
And the students, when they're entering the stuff into these cells, they have to enter them in one at a time, right?
Unfortunately, yes,
Like you have that.
no copy paste between here and Excel.
Sure.
We figured that out.
Okay.
Yeah.
Yeah. I makes it sound like I'm not very impressed. I am very impressed. I'm just having have questions also.
Yeah. The other thing I dislike about the platform, it's smart enough to know that if you did the calculation correct based on incorrect inputs, like if they missed something early on, they can say, okay, you did the calculation correct, but based incorrect input, they give you a different symbol, a calculator symbol, but they still don't give you any points. And there's no option for the instructor to say that will count for me. You have to go in and kind of add those manually if you want to do that. Anyway, any other questions?
Yes, I have a question.
Yes, please.
It's more like a feedback on the great debate that
Yes.
happened last week. So when they are estimating the size of the Milky Way, the question asks them to Google and record the true diameter. But
Yeah.
once they Google, they get all sort of numbers. The first thing that pops up is Wikipedia. It
Download?
says 26.8. There are numbers ranging from 20 all the way to 50. But the model answer is 34, which might lead to some miss autograding.
I'm hopeful that when I set up the auto grading, I was fairly generous here because I do know estimates vary. Yeah, when I did this, the estimates were a little bit higher. So perhaps they've come down with more recent, because I wrote that particular lab 2008, 9. And so the estimates may have come down. If when grading you find that once they enter 27, it starts not giving them credit, let me know, and that will be one of the updates.
Yeah, actually, what is entered is 34, and it excluded like half of their answers.
Oh, 34. Yeah, say that again. I'm sorry.
Okay, so the model answer is 34,
Yes.
and most of them used the 27-ish value.
Yeah. Now, hopefully, I set the auto grading up that it will accept, even if you say 27 is correct.
Mm.
But yeah, send me an email so it's in my to-do list, if you would.
Okay.
And that'll be one I double check when I get to updating this lab, and I'll refine it if necessary. There are two aspects of it. Yeah, thinking through this, I understand what you're saying better. They enter the true value, and I'm checking that. And so I need to check that based on a lower range, if that's lower now. And the second thing is, since they're still measuring a little bit higher value, perhaps the glob distribution is a little bit broader than the Milky Way distribution. I need to make sure that the tolerances are sufficiently generous that they won't get penalized with a larger percent error.
Yeah, exactly.
Yeah, yeah.
Okay, thank you.
Anything else?
I have a completely other random question, just because I know you're not gonna be around tomorrow. Can you give me a ballpark for how much you think it would cost for me to upgrade to like replace my dome with something that would be like reliable? You know, I mean, are we talking about tens of thousands of dollars, $100,000?
Yeah, no. So somewhere
Okay,
between those.
okay,
Um,
okay,
uh, you want to email Vladimir.
okay. I can. Yeah, you gave me his number, and I
Okay.
can reach out to him. Okay,
He'll be the best to help you with that. But
okay,
probably an Ash Dome. You could probably go to the Ash Dome site. They may have pricing.
okay.
Or if
Cool.
you want a clamshell, they've gotten pricier over the years as well.
Well, I mean, I was watching your thing on the clamshells and and the issues with the wind.
Yeah.
Um, but then again, of course, you don't have to have it rotate. So I guess there's pluses and minuses there.
Yeah, we went for the clamshells because we built the site chasing gamma ray bursts where every second mattered. And we didn't want to wait for a rotating dome. If we were to do it again, I'm less worried about that. And I would take the rotating domes for the greater protection of the mirror. I now have mirrors that have been exposed to the elements, not just sitting in
Right.
a dome, but totally exposed for 20 years. I'm
Yeah.
sure if I were to look into them, I would not see myself. And so those 16-inch telescopes are probably about 6-inch telescopes at this point. And we're working on a plan to get them recoded next year.
Right. Makes sense.
So let me just chime in, Seth. We just put in an Astrohaven dome, the clamshell variety. From our perspective, the advantage was you can put multiple piers under a single dome.
Okay. Yeah. Yeah.
So that's our plan. My guess is we're going to have for our institution a combination of Schmidt castes as well as maybe one open truss telescope. So different set of problems than what Dan just described.
And so you must have gotten a big one, not a 12-foot, but
No, so what happened is when we went to buy them, the state of California said we had to provide wind calculations so they would know it wouldn't blow off the top of the building.
Mm.
So when we called up Astrohaven, they said the smaller dome was an older product and they had no interest in doing any work on it. So we split the cost of an engineering study on their larger dome, and that's what we ended up putting in. And I didn't complain because with a larger dome, I get to put more instruments underneath it. So if you
How big
want to,
did you say, how big did you say you went with in the end?
that is a good question. My memory is poor. Let me check real quick.
Yeah, because I was thinking, yeah, I like the idea of having multiple telescopes, but I have one pier in the middle of my 12-foot right now, and I don't think could squeeze anything else in there.
and after
Yeah.
this, I'm going to have to sign out. I have another meeting
Okay.
Yeah.
nowish.
Well, while I'm looking that up, Dan, I did email with your colleague, and he seems to feel that he's more an expert on the software side than the hardware side. So I was wondering if you knew anyone who kind of knew the hardware side better, who
Yeah,
might.
Josh and May can advise on the hardware side. They're so swamped with Skynet 2, it's going to be harder to get information.
Okay.
Vladimir's selling himself short. He knows hardware and how it works. He hasn't done purchasing for a while, so but he knows like plane waves are better than Meads and Celestrons and which
Right.
he knows the yeah.
Yeah, I'm more worried about the other mechanics like cameras, computers, all the interconnect, because I basically
Mhm.
have to design something from scratch.
Yeah. Yeah, if he won't help you, you can go to Josh or May. And May's my grad student, but she's
Okay,
hardware guru. It just may be a little slower to get responses because we're deep in Skynet 2, pushing hard
I get
and
it. I
trying to
get
put
it. I get
together
it.
an emergency maintenance trip to Chile because all the mount motors died.
Oh no.
Working for like 10, 15 years, and they all die within a few months of each
Oh,
other.
crazy.
Because I don't get it. The mounts were greased. We didn't miss a greasing cycle. Just, I guess these things have a very well-defined shelf life.
Apparently.
Yeah. And so we got to get
It
them
was
up
an
and,
18-foot dome, Seth.
Okay.
yeah, we got to
Yeah.
get them up and running before the spring semester with a lot of people doing MWU and more people doing OPIS. But anyway,
Okay.
my student has been waiting for 15 minutes, and so I
Thank
better pop out and go talk to him.
Okay. See you next week.
Thanks, Dan.
Thanks. See y'all.
Thank you, Dan.